Hello, this is the EE533 Lab 4 demo. We are Group 10. My name is Chenyang Zhang, and my teammates are Zhengning Wei and Yijing Chen. And here I will quickly talk about the first three parts of this lab. This lab is about NetFPGA. We built the design, generate a byte file, and set up the environment. This is preparation for routing and network testing later. First, we set up the NetFPGA virtual machine, which is all already provided by the professor. Now we open it. After login, we can copy our generated Verilog files here, then copy them to the NetFPGA projects files here. And then we go to the scenes director. After we under the lab4 scenes director, we input the make command, and then we can see after so long time, we can see the byte file generated successfully. From the output, we can find that there are so many warnings but no errors. And finally, we get the byte file called this. Called this NF2 top pair bit. And after that, we connected to the USA VPN. This is needed to access the NetFPGA machines. We use Cisco AnyConnect and connect to the USA VPN. So this is my part. Next, my teammate Yijing Chen will continue the demo.
I'm Yijing Chen, and in this step we need to set up the NetFPGA's environment. So in this step, first we need to log in to the NetFPGA, and then we need to log in to this node 0 to node 3, and in the NetFPGA's terminal, we can use the echo instruction to know each node's address. So let's see. We can see each node have their own address, and node 0's address is 10.0.16.3, and it increased to 19. And then we can use the bit file to download to the NetFPGA, and in this step, I use the make file to make our instruction to become a more simple one. We can see make file, and so we use we use these two instruction to make it simpler. Use these two instruction, we can download the reference nic.bit and reference router.bit, and we can okay. So now we try to download the reference nic.bit, and okay. So this bit file is successfully downloaded to the NetFPGA, and as the instruction said, we can try to pin node 3. So it works very well, and to make sure each node can connect to each other, we need to try another several bit node. Okay. They can connect to each other. Okay, so now we use the IPERF to test the network performance. So we can use the node 0 first, and we use TCP mode. The node 0 is work as the server, and node 1 work as the client, and we send a message. Now we need to wait a little bit while, and node 0 should receive some message. Oh, okay. So the bandwidth is 97, and it use the 30-second receive some message. Now we test the node 2 to test if it can connect to the node 0. need to wait about 30 seconds, and then we can test the node 4. Okay, almost the same. The bandwidth is 96.9 and also use 30 seconds. Okay. So the server receive some message and the bandwidth is 97. Okay, so we just intro and now we can go to next step and in this section we can oh okay in this section we need to download the reference router.bit to the netfpga and do some tests. We need to route download. Okay, so reference router is download to FPGA, and now we can test the router. First, we need to do this instruction RKD. So 11598 is our PID, and we need to download the NIC reference NIC again, and also we need to do some network testing, and at this time we not use TCP, we use UDP mode, and we use the NF0 as the server. Okay. Uh, use this instruction to start and send a message to, for example, node 1. I think I need to uh, let's connect to node 0 and okay, so now we can wait about 30 seconds and see bandwidth. Okay, uh, now we receive some message. So the package loss is a little bit high, and the bandwidth is 35.2. This is also 35.2, and we can test another node. For example, node 0 connect to node 2, and node 2 connect to node 0. Okay, so we can see that bandwidth is 35.2, is 44.7, and the package loss uh, is 94%, and now we can do another test. Uh, in this step, we try another bit field. So as the instruction said, we need to download the router and to see the bandwidth change. So we download the router to NetFPGA, and also let's see node 0 connect to node 2, and the node 2 connect to node 0. I think I made a mistake. I think I need to add this. So now let's do some testing. we can see that the bandwidth is much higher than before. Um, this is because we use the router instead of NIC, because NIC use the PCI bus and the message is go through NIC bus and the Linux system. So there's too much depth, and in these steps we will have some bottleneck. But if we use router, anything is just performed in NetFPGA inside, so we don't need to waste so much time. So the bandwidth is much higher than before, and I think the small package stress the system is because if a normal message is one, and we just divide it to too much small package, each package need to consume some time, and you will also uh, increase some unnecessary steps, and will create some bottlenecks. So I think this is the reason why small package has it will increase a lot of stress to the system. And I think the total 4 gigabits cross wideband bandwidth is not very fair, because 4 gigabit is, I think it can it can realize in some ideal condition, but in this section we have a PCI bus and Linux system we need to go through. So uh, uh, I think we cannot reach 4 gigabytes speed. So I think the answer is not very fair. So this is all the information I think I need to include. Thank you very much. Our teammate will uh, perform another step.
Hi, this is Johnny Wei from Team 10. Today I will be demonstrating our mini IDS module integrated into the NetFPGA hardware platform. This is a record to the EE533 lab4 step 7. First, I will load our custom IDS bit file onto the NetFPGA. Here I have already loaded and make it programmed to the NetFPGA. As you can see, the output confirms that the project name is IDS. The device ID is 102 and the FPGA has been successfully programmed. Now I will start routing. We want to populate the routing tablet. Before testing the IDS, let me verify that all nodes can communicate through the NetFPGA router. All nodes are reachable, which confirms that our IDS module does not break the normal routing functionality of the NetFGA. Keys are flowing through the IDS database without being correctly dropped. Now let me check. The IDS register. Our IDS module has 4 registers: parent high, parent low, a command register, and a match counter. First, let me reset them. Sorry. Let me check the registers. You can see that pattern high is now COF414243. The top byte 07F is the validate mask, meaning all 7 bytes are active. The remaining bytes 41, 42, 43 correspond to SC characters ABC. Pattern low is 0, 44, 40, 45, 46, 47, which correspond to DEFG. The matches counter is still 0 because no traffic has been sent yet. Let me start a IPRF UPD server on node 0. Now I will send a normal UPD traffic from node 1 to node 0. The traffic does not contain our match pattern ABCDEFG. Let me also send the send data. Those and in node 2, I will send a file called bed file that contains a string ABCDEF. I will use this file as a payload for the IPRF string. Sorry, I forgot And notice the dramatic differences. Only one datagram was sent, and the client shows a warning that it did not receive a acknowledgement. This is because the IDS detected a pattern ABCDEFG in the packet payload and dropped it before it could reach the destination. Let me check the matrix counter now. Counter is no longer zero, confirm that the IDS module detected and contained a malicious packet. And let me set the node 1 as the server to try the second time. And this time, I will let node 0 send the beta file, and the other two send the normal data. We can notice that the beta file in the node 0 is also blocked as well. And let me check the match counter. The number is increased too. It shows that the mini IDS system is working well. And last, let me compare the TCP and the UDP. Let me also check test the TCP traffic. I will start a TCP server first. And first, I will send a normal traffic TCP, a normal TCP traffic. it can communicate with each other normally. Now let me send the malicious TCP traffic. With TCP, the behavior is different from UDP. The three-way handshake succeeded because the SYN and ACK packets don't contain our match pattern. But once data transfer begins, the packet contains A, B, C, D, F, G are dropped by the IDS. TCP detects the packet loss and keeps retransmitting, so the client appears to have the resulting through output is extremely low or zero, demonstrating that the IDS effectively blocks the malicious content even over TCP. And now, let me check the matrix counter. Let's see that the counter increased. Okay, that's all. That's all for our Team 10 lab4. To conclude, our mini IDS module successfully integrated into the NetFGA database. It performs real-time deep packet inspection in hardware, dropping packets that matches a configurable single byte pattern while allowing all other traffic to pass through unaffected. The IDS works for both UDP and TCP traffic and inspects packets from all input ports. That's all. Thank you.